Hello, everyone. The title of my presentation is about climate change and astroma membrane technology. Before going ahead about this presentation, I'd like to introduce myself. My name is Konung Bang, and currently I'm enrolled as a reading professor at the Department of Mechanical Engineering. The State University of New York, Korea is located in Incheon, Korea. My major is the material science engineering and earned the PhD degree from the Northwestern University in 1982. And I served as the principal scientist at the CRIS, Korea Research Institute of Standard and Science, the National Meteorology Institute of Korea until 2014. And since 2014, I joined with SUNY Korea and currently working as the leading professor. And I worked with astroma people for more than 15 years, so I know quite well about the history of the developing the world's best membrane technology for the carbon dioxide separation. Okay, this is the content about my presentation. I will briefly introduce about global warming and carbon capture storage and carbon capture and utilization, and also the general introduction about carbon capture technology. And then I will describe about why membrane technology is recommended. And then features of the astroma membrane technology will be introduced. And then I will explain to you about the performance evaluation by CAPCO and business in Philippines and cost analysis and conclusion. Well, I think everybody knows quite well about the global warming crisis. Because of the temperature rising of Earth, the people agreed the Paris Climate Agreement was made in 2015 with the arrangement of the UNFCCC, United Nations Framework Convention on Climate Change. And the target is that to keep the increase in global average temperature to well below 2 degrees C, above pre-industrial level, 5 degrees C. This is the target. And global warming is a real fact. As you can see from here, the ocean temperature is rising up very seriously. See, Indian warming, Indian Sea is at 0.7 degrees C. Atlantic Ocean and also Pacific Ocean is that temperature is rising. And probably you may think that it's quite small, but if you think about the temperature rising seriously, then we can see that the temperature is rising even 700 meter depth below. So if you think about the huge amount of the water in the ocean, then you can quickly find out that it's a real problem, the global warming. And the global warming is caused by greenhouse effect and greenhouse gas. So it's somewhat like greenhouse gas is somewhat like a blanket. So the sun sends the solar radiation, and because of the thick layer of the greenhouse gas, the radiation cannot escape to the space, so the temperature of the surface of the Earth is going up. This is called as greenhouse effect, and increased greenhouse gas is the problem. And there are several greenhouse gas, and carbon dioxide is the most serious one. And in this slide, you can see that the global temperature is going up with the increase in the carbon dioxide concentration in the atmosphere. So we can quickly find out that carbon dioxide is the cause of the global warming. And from this slide, we can find that the carbon dioxide emission has been increased since the industrial revolution around 1900s going up in total very quickly, sharply. And so the increase in the atmospheric carbon dioxide concentration resulted in global warming and climate change. It's a really serious problem right now that we have to overcome for the survival. And so some people may argue that renewable energy source may be a solution to overcome this, the temperature rising, the global warming. However, the problem is that the renewable energies contributes only 10%. So still, we are heavily relying on the coal, natural gas, or petroleum, some are like fossil fuels. So carbon dioxide emission is unavoidable for us. So until we can find the satisfactory renewable energy source or increased amount of the renewable energy source, we have to think seriously how to reduce the carbon dioxide that is emitted from the coal-fired power plant. And so the UN, as I explained to you, arranged the global agreement to reduce the climate change. And it is and according to this 2015 Paris Climate Agreement, every country should report their intended nationally determined contributions, INDCs, to the UNFCCC. And it's also, Philippines also reported about their target of the to reduce the carbon dioxide emission from the Philippines. And Philippines committed to reduce its greenhouse gas emission by 70% by 2030. It's a very high, ambitious target. And current status in Philippines shows that the energy greenhouse gas emission is mostly from the energy section, and in the energy, the electricity for the heat generation is also almost 40%. So we can think that if we can reduce carbon dioxide emission from the coal-fired power plant in Philippines, then we can quickly reduce the emission of the carbon dioxide. The situation is the same even for the United States and all over the world. The electricity generation by coal is that usually more than 1/4 for the industry sectors that the carbon dioxide emissions. And since we are focusing on the coal-fired power plant, because coal-fired power plant is the largest point source of the carbon dioxide. So strategically, it's very effective to reduce carbon dioxide if we can reduce from the coal-fired power plant. And the world electricity production in 2012, but it's still not much different even on today, 2021, is that coal is about 40% of the responsible for the electricity generation. Why we are heavily relying on the coal, even though there are so much large amount of the carbon dioxide emission? It is because of the cost. The delivered cost of the electrical energy of the coal is very cheap, followed by nuclear power plant. So many countries are still keeping or even constructing new coal-fired power plant. As you can see, the gas or wind, the cost of the electricity is higher than the coal-fired power plant. Right now, the current situation is somewhat like in the edge between that we can succeed our target or not. So this is the red line is at high emission and leading to dangerous warming. So that the 3.2 or 5.4 degrees C higher temperature and decreasing emission compatible with the well below 2 degrees C warming limit is blue line. Right now, we are in the middle between these red and blue line, so that we have to focus on how to reduce more carbon dioxide and to achieve our target. the Paris Agreement. Okay, now second, I will explain to you briefly about CCS and CCU. CCS is a carbon capture and storage. So the captured carbon dioxide is stored underneath the water or the underground. That is called as CCS. And the example can be found in the North Sea Sleipner field, the oil field, and the carbon dioxide was just stored in the oil well because there is a porous Utsira sand reservoir rock. So the carbon dioxide can be stored in the vacant area of this rock. So this is one way. It's just the storing of the carbon dioxide. And there is another application of the carbon dioxide. It's a carbon dioxide EOR, enhanced oil recovery. It's this is a method that using the carbon dioxide for the to improve the oil recovery. This is the injection well, and carbon dioxide is injected into here, and carbon dioxide is pushing this oil so that we can recover more oils. So usually the oil well can be captured from the three stages. There are three stages of the oil production: primary, secondary, and tertiary. And primary stage, we do not need any pressure because of the high pressure. The oil is ejected from the underwater, underneath of the oil field. And then from the secondary stage, we need some the force to recover the oils. So water is injected. And in the tertiary stage, it's enhanced oil recovery. Carbon dioxide is being used. So carbon dioxide is injected at the tertiary stage, then we can recover more oils. So this EOR is carbon dioxide can be used as a storage, but also can be used for the recovering of more oils. And the process is that CCU. CCU is the utilization of the captured carbon dioxide. Right now, I just explained to you about the EOR, enhanced oil recovery, but the captured carbon dioxide can be used in many other areas, not only industrially, but agriculture and food, fuel. Carbon dioxide actually had many varieties of the applications. And so if the low-cost carbon dioxide is available, then it can activate the utilization of the carbon dioxide captured. So it is the ultimate goal of the Astroma membrane technology also. For example, the carbon farming is that according to the report of the Korea Rural Development Administration Technical Research Institute, if we use carbon dioxide for the farming, by keeping the concentration of the carbon dioxide to 3 to 4 times higher than that in the atmosphere just for 2 hours in the afternoon, then the production of the agricultural product like paprika, tomato, strawberry, rose has been found that it's increased this much. So it is called as carbon dioxide farming. And this is the many other areas showing the many other areas of the captured the carbon dioxide. Enhanced oil recovery, urea yield boosting. Urea is a fertilizer. The oil and gas industry, beverage, winemaking, food processing, coffee decaffeination, pharmaceutical process, agriculture, horticulture, water treatment, and many other areas. So we can find that carbon dioxide is used in many areas. So now, what kind of the carbon capture technology is available right now? Okay, the carbon capture technologies for the power plant, for the coal-fired power plant, pre-combustion, post-combustion, oxy-fuel combustion. At this stage, commercially available technology is the post-combustion. There are three technologies that belong to this post-combustion. The first one is absorption. It is called also chemisorption. The second one is adsorption. Also, it is called as physisorption. The third one is membrane system, and it is called as physical separation. Among these three technologies, absorption has the longest history because it was developed quite a long time ago. Okay, this slide shows the principle of the absorption technology. It is well known that the amine is a kind of the chemical, has a very good affinity with the carbon dioxide. So the exhaust gas is mixed with amines. Then what happens is that amine and the carbon dioxide is combined together. And then in here, at this triple unit, heat is applied. And at high temperature, it is separated. So that we can capture carbon dioxide in here, and the amine is recirculated again to use for another continuously to use the carbon dioxide capture. And as you can see from this slide, the energy cost of this system is quite high because heating is necessary for the dissociation of the carbon dioxide from the amine. So it is called as energy penalty, and usually it's about 30% of the generated electricity is being used. It's quite large. So this is the serious problem and disadvantage of this absorption technology. Okay, at this time, the Sask Power is Canadian power plant company, and they constructed amine-based carbon dioxide capture system for the 110 megawatt power plant in the Saskatchewan. And this is the slide shows that this is the carbon dioxide capture system based on the amine technology. And another application shows the absorption process is quite well developed and matured technology. So Toshiba is proposed the amine system to capture carbon dioxide from the steel mill plant, Dongbang, the Environment and Shougang Jintang Iron and Steel Corporation in China. So it means that the amine process is quite, if the technology, TRL, technology readiness level is 9. So technically or technologically, it doesn't have any problem. But the serious problem is that it's an environmental problem. The absorption process is not promising because the amine, which is used as a solvent to absorb carbon dioxide, is very toxic chemicals. And amine is classified as a class 1 carcinogen. It means that it's cancer-causing materials, and it can cause serious environmental problem. And in the beginning of May 2010, Norwegian government decided to postpone the construction of the CCS plant based on this amine process because of the toxic materials. The problem is that if all of the amine is recovered 100%, then there may be no problem. But the problem is that 5% of the amine is released to the atmosphere. So it can cause a very serious environmental problem. This is a very serious problem right now. Okay, I will introduce you about adsorption technology. Adsorption is a carbon dioxide separation by pressure swing adsorption. So this slide shows the process of the adsorption. You see that there is 4 units, and unit 1 is carbonation, green color, and switching 1, the unit 1 become the blue color in evacuation process, and this stage 2, at the stage 3, unit 1 is a regeneration, and switching 4 unit 1 become cooling, and then repeating the cycle again. So 4 units in turn they are operating in turn, so that they capture carbon dioxide and then release it, and then other system it capture the carbon dioxide. That is the way that the adsorption process is going on. So probably you quickly understand or quickly recognize that its efficiency would not be so high. Yeah, that is true. So feed gas and the adsorption and depressurization, desorption, so that this technology has a very serious problem that its efficiency is not so high, and it is difficult to improve its efficiency because of the basic principle of the adsorption technology. So the third choice is for membrane technology. Okay, I'll explain to you why membrane technology. This slide shows the comparison of the carbon dioxide capture technology for post-combustion capture, absorption, adsorption, and membrane technology. So the advantage of the absorption is that it's simple to scale up and it's matured technology. And adsorption is a system and operation are relatively simple and less polluting compared to this absorption. And membrane technology is environment friendly, low production cost, less energy consumption. In other words, there is no energy penalty like the absorption technology. But the disadvantage, when we consider the disadvantage, then we think that the absorption is a high energy consumption and environmental pollution is very serious for this absorption technology, based. And for adsorption, it's that low separation efficiency is a problem. And it is not easy to increase the carbon dioxide purity compared to this absorption process. And membrane is the advantage is that expensive membrane, and it's not yet proved to directly applicable for large flow rate. And pre-treatment of the gas is required. Pre-treatment means that clean gas, so that all of the particles, especially dust or fine particles, should be removed because of the clogging problem. And also currently available membrane materials are not physically durable. In other words, its lifespan is short. So we think that when we think about energy consumption or efficiency or environmental problem, we know that the membrane is the best choice for the carbon dioxide capture, but still there are several problems to be resolved at this time. So according to the paper published in the 2018 in Australian team, we can find that the current membrane technologies are still on the technological TRL level 5 or 7. But so it means that commercial scale membrane technology is not yet available. Now, the Astroma technology is a TRL 9, is commercially available. So this is the unique point of the Astroma membrane technology compared to the current technologies. So it means that the Astroma is contributed to make the membrane technology as a real available technology. The critical difference between the current membrane technology and Astroma technology is here the mechanism of the separation of the carbon dioxide. The current membrane technology is based on this fiber type module, and the pore-side filtering mechanism is applied. In other words, there are lots of the pores, and carbon dioxide is smaller than nitrogen gas. So carbon dioxide is only passing through this membrane, and nitrogen is cannot pass through this membrane. So this is the pore-side filtering mechanism. And here is that hollow fiber type module. So this is the hollow fiber inside that the gas is passing through here and carbon dioxide is passing through this membrane. So as you can see from this, the photograph, find that if there is some particles or dust, then this fiber would be clogged. In other words, it cannot be used anymore. So this is clogging of the particles is a very serious problem for this mechanism. So MTR is Membrane Technology and Research Incorporation, located in California. Is one of the leading company in membrane technology, and they introduced this spiral wound type membrane. But this is only geometrical difference in the shape of the membrane. The basic mechanism is the same. So pore filtering mechanism is applied. So even if the wound system had been developed, but the flue gas should be cleaned to avoid any clogging. So it's a serious problem. And so because of this problem, the operation cost of the MTR membrane system is quite high. You see the capture cost is $33 for the carbon dioxide tons, and membrane cost is $150 for the square meters. So it's very high, it's very expensive. And so according to this Carnegie Mellon University report, that membrane-based carbon dioxide capture system for coal more than $83 per ton, even for the MTR device. So we expect that for the commercialization of the membrane technology, the cost for the maintenance cost or construction cost of technology. Okay, so I will explain to you now for the next the features of the Astroma membrane technology, and I will show you that the Astroma membrane technology overcome all of the problems. This is the cover page of the carbon dioxide capture membrane process for power plant flue gas, and final technical report reported in 2011 by the RTI, Research Triangle Institute, the International. So they studied about the membrane process, and they focused, they studied on the polymer materials with high selectivity. In here, carbon dioxide, nitrogen selectivity. If selectivity is higher, that means that carbon dioxide is separated very effectively. So polyimide or polysulfonate or the polycarbonate quite high, 23, 35, 34. And compared to this, silicon rubber is quite small. So the RTI focused the study about many about these polymer-based these membrane materials. This slide shows Robson's curve for selectivity versus permeability. As you can see, if the selectivity is higher, then permeability will be lower. And if the selectivity is lower, then permeability will be higher. So right now, people are trying to make or develop membranes higher selectivities, but we focus on the permeability. Even though selectivity is lower, if the permeability is larger, then we can have the same or the better the performance for the membrane. And we focused about silicon rubber, and we found that its solubility is 2.2 and diffusivity is 11. And so finally, the permeability of the carbon dioxide is much larger than nitrogen. So this means that if this membrane material based on the silicon rubber can be used for the carbon dioxide separation. And so the mechanism is not pore size based mechanism, but the difference in the diffusivity and solubility. So in other words, we do not need pores. Okay, only the difference in solubility and diffusivity is the basic mechanism to separate carbon dioxide from the carbon dioxide and nitrogen gas mixture of the flue gas. And we applied the specially developed catalyst to improve this solubility and diffusivity. And it was possible because carbon dioxide had a polarity. So by applying the catalyst, we could improve its performance. So this slide shows the summary of the Astroma technology. The first is that it's polarity assisted separation by nano powder coating. So there is no pores. It's very important. In other words, it can be used for the applicable, it is applicable to the dirty flue gas. Even the coal-fired flue gas can be directly used for the or supplied to the separation system. And low manufacturing and maintenance costs because of the modular type. And the third one is that the material of the membrane is very stable and durable, so that it is guaranteed to have a long lifespan. And the first is that the membrane material is stable at high temperature, and it can be operated at 100% atmosphere, H2S, the gas, or the DOST mixed gas, and no problem in the using the gas. So it can be used directly to the flue gas without any pre-treatment. And because it can be designed in modular type, so that it can be used, or it can be designed in according to the requirement of the concentration and the capture rate, and also it can be designed in a way where the limit of the construction site. So its modular type has an advantage because the module can be manufactured in the factory, and near the power plant is just the joint assembly, so that we can save time and the cost. And also it can be designed in way of preparation or series connections. So by using these two methods, then it is possible to control the carbon dioxide concentration and capture rate. The most important one is that it is not a hollow fiber type membrane in a sheet form, so that can be used for the dust, even if the dirty flue gas can be used directly. Okay, this slide shows the Astroma membrane unit, no pores and durable life and easy assembly and cleaning. You just open the door and it clean the surface of this membrane with water, and then they set up on the operation again. It's quite easy and simple. So CO2, carbon dioxide gas, is separated from the flue gas by the membrane module system. So nitrogen and carbon dioxide mixture is coming in here, and carbon dioxide lean gas and carbon dioxide is separated in here. So mixture is coming in, carbon dioxide is captured, and this nitrogen and carbon dioxide lean gas is going out. So flue gas is that composition of the flue gas is 73% nitrogen, carbon dioxide is 13%, and the water, the steam, is 10%. And these gas, even the 10% of the water is no problem. There is no pores in Astroma membrane. It's very unique properties of the character features of the Astroma technology. Okay, this slide shows the history, how the modular type or modular design of the Astroma technology has been developed. And this is currently commercial scale modules of the carbon dioxide separation, 1 meter length, 1 meter width, and 3 meter high. This module was used at the Tangjin power plant. So the advantage of the modular unit, explaining again, it provides a flexible solution to the demand of the various carbon dioxide capture capacities by adjusting the number of the modules and process stage. And also it enables shorter construction period and lower cost because the module can be manufactured at the factory site rather than on-site total construction from the carbon dioxide system. But it can be shortened if we use this modular type system. And it allows the immediate partial operation while construction is ongoing. And we do not need to wait for the full operation until the construction is finished. And likewise, enabled maintenance of the unit while allowing continued operation of other units, so that maintenance is easy. And easy operation and maintenance as the Astroma separation system is an aggregation of a standardized modular unit. Okay, the various operation modes that I explained to you that serial connection or parallel connections are possible. By applying serial connection, we can increase the carbon dioxide concentration captured. And by parallel operation, we can increase the capacity of the system. So by combining these two methods, then we can control any desired carbon dioxide purity or capture rate is possible. So we can match the demand of the customers. So the first stage, second stage, third stage, and carbon dioxide concentration is going up. It's the serial operation. And parallel operation, you can increase the capacity of the system. So this slide showed the comparison between current membrane technology and Astroma technology. Currently available membrane technology is based on the hollow fiber membrane system. It's the pore size based mechanism. And Astroma technology is a sheath type membrane and no pores. Diffusivity and selectivity difference results in the selective separation of the carbon dioxide. And membrane materials, the polymer had lower durability compared to silicon materials, silicon rubber. And energy penalty, both systems, no. And environmental friendly, yes. And membrane cost, Astroma is lower than currently available membrane technology. And the lifespan of the membrane is longer for the Astroma technology because it doesn't have a pore. And maintenance cost, as a result, is lower compared to the current technology. So Astroma technology can be described or can be said that it solves all of the current problem of the membrane technologies. So we can say, this slide shows the status of the membrane technology for carbon dioxide capture. And we can say that the Astroma technology is already in the stage of the mature technology compared to other MTR membrane technology or solvent membrane compactors or so. So examples of the pre-commercial system, everything beyond the present, and membrane system is in here also, more than 10 years. At this time, amine solvent technology is commercially available, matured technology, but the membrane is not. But the Astroma membrane technology is already in this stage. It's a commercial scale applying is possible. Okay, now it had been proved. Okay, so it was evaluated by the KEPCO, Korea Electric Power Corporation. And the performance evaluation is by the KEPCO has been done from the 2013. At the 2014, Astroma developed the membrane materials and manufactured the first prototype modules for the performance evaluation. And then in 2015, KEPCO evaluates the performance of the module for the 6 months, and they tested about the effect of the SOx, NOx, dust, water vapor, temperature, carbon dioxide concentration, etc. And then they concluded that it is very satisfactory. So in 2016, KEPCO and Astroma made an agreement to do the test in the field test for 1 megawatt scale. So 1 megawatt scale pilot plant was constructed at the Dangjin power plant, and it costs about $18 million US. And right now, field data is satisfactory, and at this time, it's a long-term performance evaluation is undergoing. So the laboratory scale type, the prototype of the modules of the which was developed at the first stage. And this is the factors that the KEPCO tested for the evaluation of the Astroma membrane system. Nitrogen, oxygen, water, SOx, NOx, temperature, pressure had been evaluated. And it was found that SOx, NOx, steam, the water content, or gas temperature, and dust doesn't give any effect on the performance of the Astroma membrane. Carbon dioxide concentration, no effect, and carbon dioxide capture rate, it does not affect it much. And dust doesn't give any code, clean or dirty. Even if it's dirty, its performance is the same. And it was found by the KEPCO that the optimal thickness of the membrane is found to be 0.3 millimeters and 0.3 millimeters. So it's very important. 0.3 millimeters is relatively thick to ensure the durability of the membrane. So it is not necessary to make it thinner. If we make it thinner, then the selectivity is lowered and carbon dioxide permeability is lowered. So it's not good. So also durability is lowered. And performance evaluation about the cost is that this one is the selectivity and this is permeability. So the MTR membrane located in here. This blue region is that the polymer membrane is the cost saving is less than 10%, this blue region. Okay, Astroma data is in here. This is pink region. So pink region is that cost saving is larger than 10%. So that we can quickly find out that Astroma membrane is much better than the MTR membranes, which is the world best at this time. So Astroma showed much better performance than MTR, the membrane. And also other membrane performance had been evaluated for the purity of the carbon dioxide captured and capture rate, and also energy consumption, as energy consumption is lower and carbon dioxide purity is better and capture rate is the same. So it had been improved by the KEPCO. And after this, this evaluation had been performed. The KEPCO and Astroma made an agreement for the joint research project for the commercialization of the next generation carbon dioxide separation membrane. And field scale construction is on this KEPCO. And you see that the 1 megawatt carbon dioxide separation is a ceremony, completion of the ceremony. And it's a Dangjin power plant, okay? So carbon dioxide capture, the 20 ton per day is 1 megawatt scale, and carbon dioxide capture concentration 96% and capture rate 90%. And construction was completed on time within budget. So it's a KEPCO Dangjin power plant. Tangjin power plant is the world's largest thermal power plant. Its capacity is 6.04 gigawatt. It's a 10 unit. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 units of the thermal power plant. And one of the this thermal power plant, this CO2 capture system of the Astroma membrane technology is applied. So this is the 1 megawatt scale Astroma system. There is control room and machinery room in here, like pumps and vacuum pump. And this is the modules. Then in the above, in here, 3 stories. So its capacity is 20 tons per day. And construction cost, the project is the $1.8 million US. And so the flue gas from the stack is captured, and then is the circulation first modules for the increased capture rate, and then is the increase the purity of the captured, so that ensures connection and parallel connection. So you can see that this is control panel, and in here you see the purity is 96% and capture rate 92%. So that the result of the field test data shows that it operates quite satisfactorily, and so it's a world first commercial application. And so the Astroma is tried to have a business in the Philippines by establishing Astroma Philippines in the Philippines, company. So the contact or discussion began in the 2017 with the Philippines CCC, Climate Change Commission. And then the commissioner of the CCC visited Korea to see that it's a real technology, and so visited the KEPCO, and this is the factory for the construction of the modules, membrane. And there was an agreement between KEPCO, 마우반시는, and Astroma G7 race. It's Astroma Philippines. And so the participants and agreement between MOU between KEPCO and the 마우반시는 Astroma. And 2017 MOA signs, okay, in Philippines. And also it was evaluated by the Department of Energy and Department of Environment and Natural Resources of the Philippine government about this Astroma technology. And it was the evaluation that it's very promising technology. And also we had a discussion with the Kaizen Power Limited, because we have to obtain the flue gas from the Kaizen Power Corporation. And so there was a discussion about the supply of the flue gas from the Kaizen Power and the 마우반시는. And it was found that there is no problem, as well as it doesn't give any effect on the operation of the Kaizen Power. And so DOE and QPR technology evaluation team visited Korea for the evaluation of the Astroma technology. And also in the 2018, the Deputy Minister of the DOE visited KEPCO and the Tangjin power plant. And 2018, technical evaluation team from the DOST of the Philippines, and they evaluate all of the performance of the Astroma, the field test, and he reported that it's very much satisfactory and promising technology. And also in 2018 is that contract signing at 마우반시는 Hall between the Astroma Philippines and 마우반시는, and about the $180 million project. And this slide shows the proposed carbon dioxide membrane capturing technology facility in Maban. This is Kaizen power plant, and this is the carbon dioxide capture facility by the Astroma Philippines. And you see here from this stack, the flue gas is connected to here through that the piping system. So composition of the flue gas is that carbon dioxide is usually 12 to 14%. And so from this stack, the flue gas is captured like here. This one is that this photo is from the Dangjin power plant. And so this captured the flue gas is processed by the Astroma Philippines carbon dioxide capture plant. And so we can separate carbon dioxide from the flue gas. And the rest of the H2O and nitrogen gas is dissipated into the air. And so this captured carbon dioxide can be used as a source for the liquefaction of the carbon dioxide and dry ice. So in 2018, it's a groundbreaking ceremony at the Ma우반시. And this slide shows the plant layout of the carbon dioxide separation facilities in Ma우반. And construction schedule is starting from 2021. And because of the unexpected COVID-19, then it's delayed. The last, before the last is the cost analysis. The investment analysis, the investment cost is $200 million US. And the interest cost is 4% per year. So that the total investment is $240 million. And revenue for a year is that $44 million per year. So the payback period is about 5.5 years. Very good to earn more money. $44 million per annually is very good return, the reward. And the US Congress reports about carbon capture technology assessment in the 2013. And I will show you some of the results reported in this report. Monoethanol amine is amine process. Absorption process TRL is 9, as I already told you many times. But the LCOE increase expected to be about 100% of the baseline. So it will depend on the report, but more than 83% or 100% or so. Vacuum pressure swing adsorption is adsorption process. This TRL is in the 3 stage because of the efficiency is not so high. And temperature swing absorption is much lower than vacuum pressure swing adsorption. And polymeric membrane is TRL in the 6. And the prospects of to reduce the LCOE increase is expected to be 30%. And now Astroma membrane, so it is commercially available and applicable for the field, the operation. So cost comparison between the existing membrane technology and Astroma technology is that energy penalty for the existing membrane technology is high, and Astroma technology is low because of the low pressure drop and low operational pressure. Investment and capital cost is high because of the high membrane cost, and construction cost is also high. But the module type design for the Astroma technology is low, and environment cost is also low, and maintenance cost is high but low. And according to this report, econoamine absorption process for 90% carbon dioxide capture would be 85.6% higher, almost 100%. Okay, so the amine process is not so much advantage. And assessment of the carbon dioxide capture cost of the carbon capture technology is the very most recent report in 2018 in Australia. And you see that thermal energy for the amine or ammonia process, absorption process is quite high. For the adsorption and membrane is no energy penalty. And also, so the plant LCOE, added LCOE for the CCS, you can see that the membrane is the lowest. So cost of the carbon dioxide avoided is that membrane is lowest at this time. So adsorption is that because of the low efficiency is the cost of the carbon dioxide avoided is very high. And it is followed by absorption, and membrane is expected to be the lowest one. So the question is that who had this technology that can show or that can match this the low cost of the carbon dioxide avoided? Okay, we see that the Saskatchewan Power is boundary dam unit number 3. It was the first grid-scale coal-fired power plant in the world to be retrofitted with a CCS system. It started with $1.3 billion, and it had been increased to $1.5 billion in 2016. So the construction cost of the Sask Power amine-based system is $1,500 US dollars per carbon dioxide ton, and Maoban project is only $1,220 US dollars per carbon dioxide tons. And the construction cost is reduced to 3/4 because in the $50 million is included in the project to construct carbon dioxide liquefying and dry ice production. And so if this cost is removed, then the cost of the carbon dioxide capture would be lower than $1,000 for carbon dioxide. Okay, another idea comparison about absorption process is technical advantage or the disadvantage challenge about the combustion, the solvent process, absorption process. As I explained to you, energy penalty and toxicity of the solvent is a problem. And for the adsorption process, the efficiency is quite low. Okay, and membrane process, it has an advantage of the no energy penalty and no pollution. But the challenge is that membrane tended to be more suitable for high pressure process and trade-off between recovery rate and product purity, and require high selectivity and good pretreatment to have a clean gas, poor economics of the scale. All of these challenges have been overcome by Astroma technology. So you can quickly recognize that why I'm saying the Astroma technology is the best technology in the world based on the membrane technology. Okay, in conclusion, carbon dioxide capture and condensing plant flow diagram is power plant, and we connect the some pipe to capture some of the flue gas from this stack. And then it's processed by this membrane-based modules, and then it's liquefied and solidified to make the dry ice. This is a process that we are going to have in the Ma우반시. And Astroma technology, it can be used for many other areas. So at this time, at the Ma우ban project, we start with the carbon dioxide separation and production of the liquefied carbon dioxide and dry ice. But eventually, it can be used for many other areas, like the carbon dioxide farming, and also refining industry, cement industry, power station, and carbon dioxide conversion technology, and also for other areas, many other varieties in food industries also. So the increased carbon dioxide fertilization in here, okay, for the carbon dioxide farming, and beverage food industry, and at this time, all over the world, the carbon dioxide enhanced EOR is the largest demand for the carbon dioxide. but also we can find many other applications of the carbon dioxide. And I expect that if the cost of the carbon dioxide is lower, then the application of the carbon dioxide will be expanded because of the low cost of carbon dioxide is available. So because Astroma technology, I expect that the cost of the carbon dioxide can be lowered by more than 30%. So this may enhance the expansion of the carbon dioxide related chemical industries, not only for the enhanced oil recovery, but other areas like chemical and biological transformation, so that we can make the plastics from the carbon dioxide, and also synthetic fuels can be manufactured, or many other useful organic chemistries can be made. So carbon dioxide utilization can be activated by utilizing the low-cost carbon dioxide supply based on the Astroma technology. So in summary, global warming is a real problem, and the innovative membrane technology for carbon dioxide capture by Astroma is available now, so that we can have a very strong tool to reduce the carbon dioxide emission from the coal-fired power plant. And we can meet the government's carbon emission allowance requirement of the Philippines government in 2030. And the Maubam project will attract the attention of the world in carbon dioxide capture once construction is finished and operation is undergoing. And we are ready to go. Okay, so patent is Astroma patent is Korean patent, register 12 pending 2, joint patent with CAPCO, registered 3 pending 6, world patent is registered 9 and pending 23. So, okay. Well, I do not know why it's not, this slide is not going on. Okay, so I think that it is time to finish it. Thank you very much for your attention. Oh, okay, here, some of the patent, Russia, Canada, Indonesia, Iran, and so thank you very much for your attention, and let's work together to save the earth. Thank you very much. The goal of the ADB is that helping the Asian countries for the development, right? And I think this membrane technology was developed in the Asian country. The fact that if ADB supports this project, then we can spread this technology for other countries in Asia, so that we can show, I mean, we can have an initiation, or we can have an initiation for to reduce the carbon dioxide emission in short time, because Astroma membrane technology is very effective technology to reduce the carbon dioxide emission from coal-fired power plant at the low cost and environment friendly. I think that this is the only solution right now that we can find all over the world. So if I wish that the ADB would recognize about the advantage of this Astroma technology and support this Astroma membrane technology to be disseminated in the Asian countries.